Okay. So if we look at the overall equation that we want to find the equilibrium constant for, we have SO2 plus NO3 in equilibrium with NO3 and NO2. And if we look at our equations, we'll see we have the second equation here. Let's number these. 1, 2, and we'll call that one 3. For our second equation, we have NO3, 2 NO3 forming 2 NO2 and O2. And in our overall equation, equation 3, we have NO3 forming NO2. So we can use equation 2, sum it up with something else, and end up with the reactants on the right side and the products on the right side. You do this with, what's it called in 12 times? When you're adding, don't you do this, what's the thing, y'all love it?
BCA.
No, not BCA. Hess's Law, yes. I was like, Hermann Hesse? No, that's not it. Hess's Law. Thank you. You're all pretty good at Hess's Law, right? Like, that makes sense? That's all this is, okay? All right, so we're going to use equation 2 as written, except for we have this coefficient of 2. We only need coefficients of 1. So what are we going to do the reaction? Half it, right? And so what are we going to do to k in that case? Take the square root. Yeah, raise it to the 1/2 power. Yep. So if we do 1/2 of 2 NO3. I'm going to leave off the phases just for the sake of simplicity here. 2 NO2 plus O2. We're going to end up with NO3 in equilibrium with NO2 plus 1/2 O2. And K for this expression, I'm going to put it in parentheses, times 10 to the minus 3, is raised to the 1/2 power. Okay, so we could figure out what that is mathematically. Everyone okay with that? All right. So then the first equation we need to adjust as well. And if we take a look at our overall equation, we have SO2 forming SO3. And that is happening, but in the reverse of equation 1. The other thing is that we only have the coefficient of 1 in front of the SO2 and the SO3. And in equation 1, we have 2. So for that first equation, we're going to need to reverse it, and we're going to have to half it. Okay? So let's first do half. So 1/2 of SO3, 2 SO3 in equilibrium with 2 SO2 plus O2. And then K is going to be 2.3 times 10 to the minus 7 raised to the 1/2 power. And so we'll end up with SO3 in equilibrium with SO2 plus O2. But like I said, we need to reverse this reaction, right? So we're going to have SO2. Whoops, I forgot my 1/2. SO2 plus 1/2 O2 in equilibrium with SO3. And what do I do to K? Reciprocal, yep, take the inverse. So that's going to be 1 over 2.3 times 10 to the minus 7 raised to the 1/2 power. Okay. Now we can take our two equations that I'm circling or putting a square around here in green. And we can add them together. And we're going to end up with SO2 plus NO3. You notice I have a 1/2 O2 on the reactant side from our reaction with the sulfur dioxide. And I have 1/2 for the reaction with the NO2. So those are going to cancel. So now we're going to have our equilibrium with NO2 and SO3. Everyone see that? Questions? Okay. So now we have to find our overall value of K. And we're going to take whatever this value is and multiply it by whatever this value is. So we'll do 1.4 times 10 to the, or we're going to do overall K. We'll do K3 because we said this was our equation 3. 1.4 times 10 to the minus third raised to the 1/2. All of that times 1 over 2.3 times 10 to the minus 7 raised to the 1/2 power. And in doing that algebra, I end up with 77.9, or 78. Questions on that? All right. Relatively straightforward, right? How do you know how many decimal points? You could follow the rules for significant figures and work through all of that. Let's see, we're multiplying and dividing here. So whatever I forget the rules off the top of my head. Is it, what do you keep the same number of decimal places? I never use these rules. I find them irritating. And then they've left my brain because of that. They are irritating. The rules for sig figs harken back to a time when we measured distance with rulers and we measured volume with like rather imprecise instruments. Like all of those significant figure rules harken back to a time when we had rather imprecise things to measure with. So that's why it just drives me nuts. Okay, so we talk. Oh yeah, sorry, Brady. Okay. All right. So last time we talked a little bit about equilibrium constants when we're using concentration, and those when we have pressures. And we can relate an equilibrium constant that's in the form of concentration, moles per liter, to those in pressure, namely atmospheres, by the equation Kp equals Kc times RT raised to the delta N. Okay. So this relationship is going to allow us to switch from an equilibrium constant that focuses on concentration to one that focuses on pressures. You may want to do that for some reason, so we'll show you how to do it. Okay, so I think last time we calculated the equilibrium constant for our ammonia formation, our equilibrium for that at 573 Kelvin, and we found that K is 9.60. So using that, we can calculate K sub P. So if we look at our equation, again, we're solving for K sub P. We know our K sub C value, that's 9.60. We know our temperature, and it's in Kelvin, that's important. And we know R, it's in liters times atmospheres over moles Kelvin, which is going to allow us to go from a concentration to an atmosphere. So we'll have 0.08206 times our temperature in Kelvin. That has to be in Kelvin, 573. But kind of the tricky thing here is the delta N. So the delta N is the sum of the coefficients of the products minus the sum of the coefficients of the reactants for only the gaseous species present. So if we're going to work in a equilibrium constant with pressures, the only thing that's going to affect the pressure are gases. Right? So only the gases are going to make a difference here. For our equilibrium with ammonia, everything's in the gas phase, so all of those, the reactants and products, will count. And so we look at the stoichiometric coefficients. So for the product side, we have 2. And for the reactant side, we have a total of 4. So we're going to take the sum of the coefficients of the products minus the sum of the coefficients of the reactants, and we'll end up with minus 2 for this example. Okay. So we can replace our delta N. And I don't think I've calculated this in my notes, so we're going to have to do that together. Oh, no, here it is. Okay. So K sub P equals 9.60 times 0.08206 times 573 times, raised to the power of minus 2. And I end up with a value of 0.00434. All right. Everyone okay with the calculation? So there will always be a gotcha problem, of course, right? A good example here is calculating this delta N. And again, the main thing is that we only include those things in the gas phase. So if we have a reaction where we have A plus B in equilibrium with C plus D, and A is aqueous, and B, C, and D are all in the gas phase, for this delta N calculation, we only care about B, C, and D. We do not care about the A because it's aqueous. Okay? So in this case, delta N would be, let's see, we have 2 plus 1 on the product side, and we have 1 on the reactant side, so it would be 2. Okay? So watch those phases, they are important. All right? Make sense? Invigorating? Yes, I can tell. Okay. Let's go back to this problem that we were working on. Did a few different things with this one. Here we have a reaction that is, if we recall, A2 plus B in equilibrium with A2B. If we assume that everything is in the gas phase, someone asked me about that last time. How did I know they were in the gas phase? I must have done part D. Assuming that everything's in the gas phase, calculate delta N that accompanies the reaction. So take a quick look. What do we have? We have a coefficient of 1 for the products, minus 1 plus 1 gives gives us -1. Okay? So we could then use a value of K sub C that we calculated previously in this problem. We said that K sub C was 40, and we could calculate Kp. And assume we're at 25 degrees Celsius, or 298 Kelvin. Some people usually ask me, why do I leave off the 0.15? So you're at temperature in Celsius plus 273.15. Again, mostly just laziness. And I don't think I've ever run into a problem where I didn't include the 0.15 and it made me get the wrong answer. So if you feel like being lazy, I think this is a place where it's acceptable. Okay, so calculating Kp for this reaction, we're going to have our Kc times R times T raised to the delta N. So we'll have 40, that's 0.08, 206, oops, times T, which is 298 Kelvin, raised to the delta N, which we just said was -1. And so we'll end up with 1.64. So 1.6. Yeah.
Where did you get the KC equals 40 again?
Kc equals 40 is from the example that we did last lecture.
Okay.
Yeah.
So it can change. Like it is.
Oh,
We're just using it for this example.
for this example, yeah. So we calculated using this example. Yeah, this is like step E, part E of this problem.
Okay.
Yeah. Yep, no problem. Yeah. So, but kind of leading into that. So you asked if K could change. So keep in mind that and maybe we haven't really done this yet, but our equilibrium constants K, they are going to be dependent on temperature. Okay. So keep that in mind. Whenever you see a problem that's going to say at this temperature K is this, at the same temperature, calculate whatever it might be. Okay. Questions on that? All right. So thinking more about what K means. Oh, yes, sorry. Is temperature the only thing that affects K? No, it is not. So when we talk about Le Chatelier's principle, no, I take that back. Temperature element. Go in there. There might be some other things, but that's in the beginning of No. So not really that. So K is going to help us figure out equilibrium concentrations. So we could start with whatever a concentration of, for a reactant, let's say a decomposition, we'll start out with 1 mole per liter. And we'll end up with an equilibrium concentration, and we can figure that out based on K. If we start out with 10 moles per liter, we'll figure out a new equilibrium concentration. That K is going to be the same unless we change the temperature. Yeah. Okay. Anything else? Okay. So thinking about our equilibrium constant and like what it means in terms of concentrations of reactants and products. So we typically are we're gonna see values of K that are large or greater than 1, and we're gonna see those that are less than 1. We don't have negative values of K. And so if we have a large value of K, we're going to say that that reaction is product favored. Your book will often say that equilibrium lies to the right. I think we've discussed before that I often get left and right confused, so I will say equilibrium is at the product side or reactant side. The chemical reaction is product favored, meaning there's more products at equilibrium than reactants. So I'll just avoid using left and right. but keep that in mind. What those left and right mean in terms of left is reactants, right is products. Okay. If K is less than 1, it is reactant favored. And so you'll end up with more reactants at equilibrium than products. So we saw when we were talking about lead in drinking water with regard to Flint that the solubility of lead phosphate was very low. I think it was something times 10 to the minus 44. That's a very, very small number, K less than 1, right? And so heavily reactant favored. In that case, the reactant was solid lead, not the lead that was dissolved in water. Okay? Okay, questions on that? Okay, so that, oh yeah, sorry.
How close to 1 does it have to be like considered like equal?
Yeah, so if K equals 1, there are equal numbers of reactants and products. I don't think we're ever like, we're never going to give you a problem where we're like, K is 1.01, you know, is it reactant favored or product favored? That's not a fair question. Yeah, it's usually a bit more obvious. Anything else? Okay. So,